Alright, so most asteroids are found in the asteroid belt, which lies between the rocky planets and the gaseous planets, so somewhere between Mars and Jupiter. So if you're looking here at the representation in the slide, the rocky planets will be Mercury, Venus, Earth, and Mars. The gaseous ones, Jupiter, Saturn, Uranus, and Neptune. So the asteroid belt lies right between Mars and Jupiter. So asteroids are composed of rock material, metallic material, or rock metal mixtures. So they would pose absolutely no threat to Earth if they remained in the asteroid belt. However, as they move around the belt, they collide or bump into one another, as you can tell in the image and in real life. There's many of them, so the likelihood that they bump into each other is relatively high. And as they do that, it causes some of them to be in orbit or move out of orbit that then would intersect Earth's orbit, so potentially being harmful to the Earth, so impacting the Earth. And the same goes for all the other planets nearby. If an asteroid is bumped and suddenly intersects the orbit of another planet, then that planet is likely to be hit by that asteroid. So when asteroids break into smaller particles, which may range in size from dust size to a few meters in diameter, we call them meteoroids. So if meteoroids enter the Earth's atmosphere, it becomes a meteor. Okay, so they are the same in terms of nature, but they have a different name. So meteoroid, when it's an asteroid broken up from dust-sized particle to a few meters in diameter, it's a meteor when it enters the Earth's atmosphere. You might also have heard them called as shooting stars, which are called this way because the frictional heating of the meteors as they streak through the atmosphere produces light. And we'll look at this a little more later. And if that meteor impacts the Earth's surface, then it becomes a meteorite. Okay, so again, they're all the same in terms of composition and size, but they change in name depending on whether it's impacted the surface of the Earth, is just in the atmosphere, or if it's outside in space still. The last type of particle that we'll talk about here are comets. So comets are distinguished because of their glowing tail of gas and dust. So they range in size from a few meters to a few kilometers, or hundreds of kilometers sometimes. And we believe that they are made up of by a rocky core that is surrounded by ice and by carbon-rich dust. So as the sunlight heats the comet, the dirty ice full of carbon particles will evaporate to form a mixture of gases, which is why they have that tail behind them. Comets are thought to have originated beyond the planet Neptune and to have been thrown into the Oort cloud, which lies between the Kuiper belt that extends as far as 50,000 times the distance from the Earth to the Sun. So here you have Neptune, here is the Kuiper belt. I'm not sure how you say it. I think it's Kuiper, but it could be Kuiper belt. I'm not sure. But that's the Kuiper belt. And then again, the Oort cloud, where the comets actually have formed, extends between, again, Neptune and about 50,000 times in distance from the Earth to the Sun. So it extends very, very far away. So that's where we believe that comets are thought to have originated. Okay, so when asteroids, meteoroids, and comets enter the Earth's atmosphere, they travel at a velocity of about 12 to 72 kilometers per second. As we saw in the last slide, the composition of these bodies differs greatly, but those that have a stony composition are differentiated, meaning that they have undergone igneous and sometimes even metamorphic processes as part of their geologic histories. So again, those would be the ones that have a stony composition. If you're, again, more curious about which have a more stony composition versus metallic or gaseous, go to table 14.1 of your book. So once comets, asteroids, or meteoroids intersect the Earth's orbit and enter our atmosphere, they undergo remarkable changes as they heat up due to the atmospheric friction. And so this atmospheric friction happens during the descent, and it produces a bright light that is basically heat being evaporated, or water or any particles being evaporated from that body. So for example, a meteor that is entering the Earth's atmosphere and is about 85 kilometers above the surface will become a meteor, right, as it does this, and will emit light. It will then either explode as an air burst in the atmosphere, and they typically explode in the atmosphere at an altitude between 12 and 50 kilometers for them to be considered air bursts. However, they can explode pretty much anywhere above the surface and still be considered air bursts. Or the other option that it has as it's coming down towards the surface is actually collide with the Earth's surface, hence becoming a meteorite. Okay, so there are two options for that body. One is explode before it impacts the Earth, in which case it's going to become an air burst. And then the second option that it has is to actually collide against the Earth's surface and make a crater, in which case it's going to become a meteorite, or the remains from it are a meteorite. Okay, so many meteorites have been collected around the Earth, especially in Antarctica. The Tunguska event that happened in June 30th of 1908 is a very good example of a large airburst from the modern era. So this didn't happen too long ago in historic time or even in geologic time. And so it's a very good example of an airburst. So again, this was called the Tunguska event, as you're seeing here. And it happened in Siberia, Russia. So witnesses reported seeing a white-blue kind of fireball with a glowing tail that was descending from the sky. That fireball exploded above the Tunguska River Valley in a heavily forested area with very few people, which was very lucky. Later on, the calculations showed that the energy that was released from that explosion, again, that was an airburst, so a little bit above the surface, released from about 10 megatons of TNT, which is equivalent to about 10 hydrogen bombs going off. So that gives you an idea of how huge this explosion must have been, even though it was a relatively small body and it didn't actually impact the surface. So that tremendous blast, it caused trees in an area about 200 kilometers squared to actually be flattened and be burned. Some of the witnesses, tens of kilometers away, said that they were physically blown up into the air and they were completely knocked unconscious. And then later on, they woke up in a completely different landscape. Well, obviously, as you could have imagined, if the trees 200 kilometers squared away from the airburst site actually became flattened, I'm sure that they must have been, amazed about where they woke up when they did. So the blast was determined to have been heard throughout an area of 1 million kilometers squared. So if you were, for example, pretty much in any part of Russia, and even in some parts of Europe, you should have heard the explosion go. And since no crater itself was found by geologists or by any other Russian scientists, they calculated that the explosion must have been, again, an airburst of about 25 to 50 meter in diameter, of a meteor that was 25 to 50 meter in diameter, and that it exploded about 7 kilometers above the surface. So to give you a perspective, 25 to 50 meters is about, 75 to 150 feet. So it's large, but it's not nearly as large as you could expect. So a relatively small meteor exploding 7 kilometers above the surface. 7 kilometers is like 4 miles, 4.5 miles or something like that. it created that much damage, you can just imagine what a bigger body could have caused, and one that would have exploded closer to the surface or even at the surface that would have impacted completely. So that is one of the most recent events that we have to compare things to. So again, we were very lucky that this event occurred at such a sparsely populated area. Otherwise, we would have probably encountered major economic consequences, and we would also have encountered a major loss of life if it happened, say, in Tokyo or even in Moscow or St. Petersburg or something like that, closer to the site. So it is estimated that an event such as Tunguska, if it occurs again, or it will occur again, it occurs once in every about 1,000 years on Earth. So that is the recurrence interval that such an event has on the Earth. So yeah, that is good to know. All right, so the most direct evidence for impacts on the surface comes from studies of impact craters that they produce. So worldwide, there are more than 175 individual craters or small crater fields that we have found at the very least. So from those, we can examine the evidence that is given from the actual bodies. So the best known case, at least the best known case in the US, is probably the Beringer, I think it's Beringer crater, which is in Arizona. So this is the crater itself. This is a 49,000 years old bowl shaped crater, as you're seeing right here, with a diameter of 1.2 kilometers, so that is the length right here, and with a depth of about 180 meters. So that is how high this is. And the rim itself rises 260 meters above the desert, so this is already much risen from the remaining part of the desert. The rim itself is overlain by an ejecta blanket, which is really just a layer of debris, which is kind of material that was ejected from the crater upon impact. So you're seeing here in the image below a cartoon depiction of the amount of ejecta blanket, the amount of debris that is on top of the rim itself. That is what's creating the rim itself, giving it so much more material to be risen above the desert. And much of the material that is actually inside the crater is also debris that fell back inside, or material that collapsed from the walls. So as you're seeing again over here, the crater used to be much deeper, and much of the material inside of that crater is actually material that used to be either on the walls, or that as the impact happened, it ejected a bunch of material up and then it fell back inside of the crater. So the initial crater was probably actually much deeper than what we see today, as is depicted again on the image here below. After much studying of that particular crater, of the Beringer crater, it was found that the crater was formed by an impact of an asteroid about 25 to 100 meters in diameter. It took many years because there are other geologic processes that we can find craters in to actually determine that this was caused by an impact. However, the impact craters, are different from other craters, and that's how they were able to do it. So impact craters are characterized by containing some metamorphosed rocks, for example, as well as mixing of melted rocks with some of the material from the impact object. So these features are caused by what is kinetic energy transfer into the surface. So kinetic energy is the type of energy also referred to as energy of movement. And so that energy of movement is what causes the metamorphic rocks to occur, as well as those melted rocks to be mixed with whatever material the object was made out of. So I also wanted to point out the impact craters that have been found at least in North America. So here there are over, I think, 30 at least impact craters that have been found. The Beringer crater one is this one right here. Another big one that we'll be touching on later is this one right here in the Chesapeake Bay. And then another one in Quebec that we'll be talking about later as well. So as you can see, they're not uncommon, at least within the continental crust. The oceanic crust is a little bit different, but they're not really uncommon, and that's how we've been able to study impacts in the recent 100 years or so.